Doppler effect is a motion-related frequency shift which was originally proposed by physicist Johann Christian Doppler. It was then tested experimentally in 1845 using a train engine which pulled an open car with several trumpeters. So here I'm sketching a locomotive with a trumpeter and it's moving. So the premise behind the Doppler effect is that when you have a source emitting sound, and then that source is traveling, as the source travels a distance, that sound wave, so the purple sound wave traveled a distance related to the speed of sound, while the source emitted another wave. Then as that continues to move, what you see is that the waves sort of pile up in front of the source and stretch out behind the source, because the source is moving at the same time it's emitting the waves. So the detector in front of the source is perceiving a shorter wavelength or a higher frequency, while the detector behind the source perceives a longer wavelength or a lower frequency. And I'm sure you've experienced this whenever you hear an ambulance approaching your car or driving away from your car. You can hear the change in the pitch of the siren, or a train if it blows your horn while it's coming toward you. So for the situation where the detector is stationary and the source is moving, we can calculate what the wavelength measured from the source would be. So lambda is going to be the wavelength that would be measured if the source was stationary, and lambda prime will be the wavelength measured when the source is moving at a speed u in a medium where the speed of sound is v. So the time between the wave crests would be the period t, and during that period t, the source moves a distance ut, the velocity of the source, times the time. So the new distance between the wave crests would be the new wavelength. Alright, so if we had a stationary source, the distance between the wave crests would just be lambda, and they would just be evenly spread out like that. But now when the source is moving, so the source is the black dot, it moves a distance ut and emits a new wave. But in that time period, that first wave has expanded out, and the distance between the two waves is going to be velocity times time, the velocity of the wave, and that distance is also equal to the wavelength. We want to measure lambda prime, which is going to be the distance between the old wave and the new wave. So from inspection of this diagram, you can see that lambda prime is just going to be the difference in lambda minus the distance that the source has moved. We know lambda is equal to Vt, so we can solve for t and get lambda over v. We can then factor out lambda, and if we have a minus sign like we did before, that is when the source is approaching the detector. And the same thing holds for the source receding or moving away from the detector. The only thing that changes is the sign of the velocity, so you use a plus sign. So we have those two situations for when the source is moving and the detector is stationary. But usually we recast this in terms of frequency f. We know that lambda is velocity over frequency, and lambda prime would just be velocity of the wave over frequency prime. So we just replace these with frequency. The velocities cancel out, and we solve for frequency by cross multiplying, but usually we look for f prime because that's what we would be measuring. So I solve this for f prime, and I get f over 1 plus or minus u over v, where u is the speed of the source and v is the speed of the wave in that medium. So as a general rule, whenever the source is approaching you, you're going to detect a higher frequency because the waves, about the waves piling up. If the source is receding from you, you're going to perceive a lower frequency because the waves are being stretched out. There's another situation where the detector is moving and the source is stationary. And in that situation, the wavelength doesn't actually change, but the source is actually running into the waves at a faster rate, and so it seems like a higher frequency. So if the detector is moving into the wavefronts, the rate of interception is greater, so we get a higher frequency detected. So here the orange is the distance between the waves, that's lambda. Here we have the speed of the observer, which is u, moving toward the source, and the speed of the wave in purple is v. So we want to know what the number of wavelengths intercepted would be, and if you're in the frame of the observer, the green dot, then the wave velocity is going to be v plus u, and so the number of waves you're going to perceive would be v plus u times the time, so the distance, divided by the wavelength, and that would get you the number of wavelengths intercepted. We want to know the frequency, so we take that number of wavelengths and divide by time. The times cancel out, and we get v plus u divided by lambda. But remember that lambda is just v over f, so we can plug that in, and we get 1 over u plus v times the frequency is our new frequency prime, and that's for the detector approaching. And you just change that to the minus sign for detector receding. So we can actually put this all into one equation, the general Doppler effect equation, where f prime is equal to f times v plus or minus the speed of the observer divided by v minus plus the speed of the source. So this would combine both moving source and moving detector. And basically, if your detector is approaching the source, you know that the frequency should be higher, so you're going to choose the positive sign in the numerator to make that number bigger. If the detector is receding, you know that the wavelength or the frequency should be smaller, so you're going to choose the minus sign to get a smaller number in the numerator. In the denominator, if the source is approaching the detector, you know that the frequency should increase, so you're going to choose a minus sign to decrease the numerator or the denominator. And if the source is receding, you know that you should have a smaller frequency, so you're going to choose the plus sign to increase the denominator. Note that all speeds that we talk about here are measured relative to the medium.